about Newton's constant. And the way we have written it was in like completely useless units. So let's write this Newton's constant in a somewhat better, more useful set of units like this. It's given by G by C to the 4 is H bar C times 6.7 times 10 to the minus 57 EV squared. Okay, so this is, no, sorry, EV to the minus 2, like this. So if you use this, then the Planck mass is given by this 6.7 times 10 to the minus 57 to the 1 half EV over C squared, and this is what we are accustomed to, 19 GeV over C squared. We have already seen that the Planck time, which is LP by C, and the Planck length was given by H bar G divided by C cubed to the 1 half, 1.61 times 10 to the minus 35 meters. Of course, you can express this in femtometer. This is 10 to the minus 20 femtometer. And when you put this in here, then you get points. Yes, that's right. And this, the Planck time we had already seen was 5.41 10 to the minus 4 seconds. So the way to think about this is, if the Planck mass is sent to infinity, that means that we don't ever have to worry about gravitational interactions. So you can see it from these things that this is an awfully small number. Of course, small and large doesn't make any sense unless you have the scale in the problem. Nevertheless, we have other scales in the problem, such as the electroweak scale and so on. So if you compare it with the electroweak scale, and if you let the Newton's constant go to 0, evidently this means that the Planck mass is set to infinity in that limit, and then you don't have to worry. This also means that in the same limit, the Planck time essentially is gone to 0. That means that you never had a Planck error. So that's another way of saying that you don't have to worry about quantum gravity. Or you can say that the Planck length goes to 0. That means you never have to worry about the length scale in which you ever have to worry about Planckian effects at any length scale if you send it to 0. So many of you have been sending me all kinds of questions about what is going to be taught in this course, what is the syllabus, all kinds of very boring bureaucratic questions. It's like if you go to a movie, you don't want to know what is going to come after 1 hour, what's going to be the ending of the movie and all that. Now, if you have that kind of approach to films, you should also have the same approach to your course. But since I want to forestall such boring questions for the rest of you, for the rest of my life, let me tell you what I'm going to do. I'm going to basically follow the set of topics, not necessarily in the same order as from the book of Grossman and Neve. You don't have to ask me what this book is, because I already sent you a picture. You can look up in that what these are. So various things that we need in order to construct the standard model, and we already mentioned this the other day, is we need Lagrangians, and Lagrangians that involve scalars, fermions, and gauge bosons. Okay? So we need to worry about these things. These are the degrees of freedom as far as we are concerned. And typically we will also be concerned with symmetries of Lagrangians. Symmetries of Lagrangians. And what is the language for studying symmetries? Does somebody know? Somebody has to volunteer these answers. Yeah, right. So we will use some ingredients elements in group theory, which is the language in which we discuss these things. So symmetries, of course, come in two varieties: the continuous and discrete. And the discrete symmetries that will be of importance to us are those that are present in the special theory of relativity, and mainly this will be parity, charge conjugation, and time reversal. Occasionally, there will be a joint action of C and P and C, and this is called CP, and this is closely related to time reversal invariance. So this would also imply if there is CP violation present, and this we will see later how this works. This will imply that some of the couplings in the Lagrangian complex. So one implies the other. And we had already mentioned that the kinds of symmetries that we will look at either abelian or non-abelian. And by abelian symmetries, we mean that the group elements will commute, they're commutative, whereas in this case it's not. Not only that, symmetries will be of two types. One is called local symmetries. These are called local, or what we call gauge symmetries. These are all again historical names. This name, gauge symmetry, was given by Weil long ago, and it's just a name that is stuck. It doesn't mean that it's a gauge, like in a fuel gauge or something like that. In a sense, it is, but you don't have to worry too much about that. And the existence of continuous symmetries is related to conservation laws. And this follows from Neuman's theorem. However, the standard model, there are some conservation laws, and nobody knows what those symmetries are. There are some conservation laws. Can somebody name a conservation law for me? I don't mean space-time things like momentum and angular momentum, but there are conservation laws like lepton number and baryon number. Not only is it lepton number, but lepton number of each type. Each type is somehow conserved. In other words, there is no transition of a muon to an electron plus gamma. There is no such state. Okay, never observed. There's an experiment which is trying to see it, and it's called MEG. Why is it called MEG? Muon to electron and gamma. That's the name of this experiment. Okay, and what it does is it gives you all kinds of constraints on this kind of array process. Okay. You all okay? Is it a bit stuffy over here? Open the window at the back. There's some other virus going around. That's why I'm not using the air conditioning. Just open the windows so that we have some ventilation here. Then there's a chapter in this book on abelian symmetries. Abelian symmetries. And I guess abelian continuous symmetries. Continuous gauge symmetries. But I won't be doing all these things in a hurry. I first want to introduce you to many of the phenomena that the standard model is going to try to explain so that we get acquainted with what it is that the standard model is supposed to do. Now, I'm going to stop here, pause here, and ask you a question. How many parameters of the standard model have we encountered so far? 90. So far in this course. Yeah. In other words, in lecture 1. Okay. This is for the benefit of your friends or enemies who will come to the first class. Okay. So, can you hear the first class? So we can't ask you. Okay. Name one of the parameters we ran into in the first class. You don't have to look at your notes. Electric charge. Okay. Definitely one. Okay. E is one of them. What is the other? Mass of the electron. And we said that this is actually enough to describe QED. Okay. QED is the purest of the pure theories. It has only two species of particles. It has an electron and it has a photon. And a photon, and it there's only one vertex. Okay, and it has only two parameters. Such a beautiful thing. However, we said that there are heavier cousins of this electron, and what are those? Muon. So of course there is the electric charge is the same, so I don't have to mention any. There's no other. It's not as if the muon is going to carry a different charge. Okay. So there is also mass of the muon. Anything else? Mass of the tau. Can somebody tell me what the mass of the muon and the tau is? Okay, so I said I'm going to ask people to volunteer, look at Google, and tell me what these things are. Now, if I keep writing things and you just mechanically keep copying these things, you're not going to remember any of this. Okay? So, please tell me what is the charge of the electron? Charge of the electron in coulombs, but of course we always put it equal to 1. Nevertheless, at least once in our life, we should write down what this is. What is it? 10 to the minus? 19 what? Okay, mass of the electron in a sensible units, not nonsense units. Okay, mass of the muon 105.6 is good. We just keep it to one significant case. And mass of the tau 1.78 actually. Yeah. What? G. Isn't that amazing? That in a theory with just these leptons, you're having all scales over here. You're starting with a, okay, less than an MeV, 100 times an MeV, and a GeV. See? Why? Why is it that you have so many, so many different masses?
Generations.
Yeah, so?
QED does not tell us that.
Nobody knows. Nobody knows why these masses are what they are. These are just experimentally known. Okay? So, but already, since you people are so clever, you have found for me already 4 parameters of the standard model. You people also mentioned something about neutrinos, right? So, mass of the this, mass of the mu, and mass of the tau. Any idea?
Less than 0.0.
Consistent is 0.
Hmm?
Consistent is 0.
Consistent with 0, but
Less
present day limits. Actually, it's no longer the case. We know at least 2 of the mass differences are non-zero. Okay? Of course, it doesn't rule out the possibility that one of them is identically 0, and those mass square differences are the masses of the other 2. Okay? But the most general cases, all 3 of them have masses. The mass square differences are known. Okay? So, what are these? Somebody tell me.
So less than 0.1.
Yeah. Or you ask your friend to come and do it. Okay, doesn't matter. Okay. 0 point.
1 E.
Are you sure? Where did you look this up? No, no, we want reliable numbers, so please look up the latest from
Differences
particle.
around, differences card is around.
I don't want around. I want you to look at Google and tell me the number. Okay. Now, if I keep writing all these things, people will not remember. That's the reason why I'm sure you'll get me for it. I don't get it. Hmm? Sure. Less than which one? Okay, then. See, this is ridiculous, isn't it? Isn't it? This is EV scale. This is MEV, GEV. I mean, we have 9 orders of magnitude over here. Why? Nobody knows. Okay. Then we own neutrino mass. Less than 150 keV. See? See, unless we think about this, we will not see the appearance of all these different scales. Okay, then the tau.
I think it's 150.
Yeah.
15.5 MeV, she said. Is this from AI or is it from a reliable source? See, Google also is now just giving you guesses from various AI, large language models and all this. So we want reliable. Any reliable source here? What does it say?
electron usually says 0.05 electron, less than 0.05.
See, that's why I asked you. Yeah, come in, write it correctly here. See, this AI these days also the first hit on Google is some AI generated stuff. So we can't really be sure. Yeah.
Actually, there are 2 points. One AI is saying 10 maybe, but it's.
Yeah. Go. Yeah. What? Windows 7? Yeah. Units. Okay. But that's okay. Earlier it was 0.1, which is same or just around now.
No, it's not 10.
Oh, 10. That's why I was not convinced by that number. See, this is really what it is. Hmm?
As far as I know, we know the mass eigenstates, not in the favor states. The mass eigenstate is less than 0.1.
This one.
Overall. No, I think it's overall.
Okay.
Overall,
All of them are less
individually,
than.
I think we don't know right now.
Okay, so you put this. Put a-
Actually, I mean, it's not this.
Now that'll take a little bit of explaining why you have written it like that. This way and this way. Every one of them.
Actually, we don't know the values right now. As far as I know.
Okay, so this is according to Jaya. Okay.
Not
So
correct.
you're all urged to go and check this for yourself.
You can
I think sum of all three are.
These things are 0.8 electrons.
Yeah,
G
some
puts
of
a limit of 1.1 electron volt on electron.
Is
Okay,
okay, folks, you figure it out for yourselves. Okay. But what is interesting or important is what she has introduced over here. She has sneaked in something. She says that you're no longer allowed to call it separately E, mu, and tau. And she has said that there's some other principle over here. And she has said implicitly, without saying so, that there is something going on in the neutrino sector, and this is called mixing. Mixing among neutrinos, which is due to presence of masses. Okay? Presence of masses. It's easier to understand this in the quark sector, as we will do a little later, but the concept, the notion of mixing among these things has already been introduced for you. And the mixing parameters, which again we need to list for the standard model. So there will be 3 mixing angles, and 1 or 2 phases. Okay. Now this is a qualitative lecture, and that's the reason I'm telling you this. Why 1 or 2? See, these electrically neutral particles have a peculiar property that they can be their own antiparticles, in which case the governing equation for them is something known as the Majorana equation. Majorana. And if indeed neutrinos are Majorana particles, then the so-called mixing matrix is more general, in which case you can have 2 phases. And what are these phases good for? Yeah, so here we already mentioned that couplings in the Lagrangian are complex, which means that if they're complex, they have a modulus, and then they have a phase. And if there is a phase, that can lead to CQ violation. Okay. So good. So here, how many parameters have we found already? 1, 2, 3, 4, 5, 6, 7, 10, maybe 11 or 12. Okay. Now, any other particles you know, and any other parameters that you can figure out? Wait a minute. So what are the other particles? Let's name the particles first of all. The other day we did that already, and we said that you have a UV, you have a CS, and a PB, and just as in this case, we don't call it D assembly, but actually we have a D prime, and the D prime, which is for the mixing. So how many parameters do you have? 6 quark passes. And how many mixings do you have? Mixing. 3 angles and Three angles or one phase. One phase. That is because of the transitions between these. And what are these transitions due to? These transitions are due to the weak interactions, right? This is what you people have learned in your previous courses. So this is the charge current, weak interaction, weak interaction, which is transmitted by VW plus. So just as you have the transitions between mu, mu, tau, tau. Okay? And since you already said it like that. And the same weak current interaction causes transition. Very good. So I mentioned something about the weak interaction. So what does that mean? That means that there is a coupling between, let's say, a neutrino and an electron, L, and then there is an interaction like this, which is a W, okay? Which means that there should be a coupling constant associated with that, and that coupling constant is G. Of course, you can also have a coupling interaction between a U and a D pipe, because W is also defined. So these are the vertices of the charge current weak interactions. Vertices of the charge current weak interaction. If there's a charge current, what is contrapositive of the charge current? Some current that is not charged is neutral. So here this photon is an example of a neutral current, and this is not the only one. There is a weak neutral current also, weak neutral current, and that is transmitted by. So you can have any one of these particles. And then later we have to figure out what is the coupling constant. So here you see here is one more coupling constant that we have sneaked in over here. And of course we have the strong interaction where we have QA, QB interacts with the gluon, AB bar, and then there's a G strong. So this is another of the parameters of the standard model. Okay. GS, which is the cousin of the electric charge, what the electric charge is, the electromagnetic interaction, or what is G for the charge current weak interaction is GS. I think we are more or less out of all the standard model parameters. There's another one, very peculiar one, which is called theta parameter of the strong interactions. Which has to do with the vacuum and the instant on, etc., etc. And it leads to something called the strong sweeping problem. So when somebody asks you what is meant by the standard model is a theory of interaction, so all these particles, leptons, quarks, and the interactions among themselves, and these are all the parameters that appear over here. Except that there are other self-interactions also in the non-abelian sector. There are also interactions. For instance, the gluon will have coupling like this. The gluon will have coupling like this also. Has a cubic as well as a quartic. So this will be a GS and this will be a GS squared. So this will be cubic as well as a quartic. Of course, you may ask, and correctly so, why should the GS here be the same as the GS over here? After all, this is the coupling of the ought to the gluon there is the self-interaction. It is so, okay? In order for the structure of these theories to make sense, it's the same coupling constant that has to show up here also. Okay, good.
So we get a theta term for the Maxwell part and the weight part.
No. It has to do with, you ask an important question, and I have to think a little bit about it, but there isn't one. I don't know exactly why, and I have to think about it. Definitely for the Maxwell part you will not have, because you cannot write a structure that involves a dual of the electromagnetic field tensor. But let me not give a wrong answer. Think about it.
So can you repeat why the interaction term is the same?
I didn't give you the reason. Okay? I'm just telling you that that is the case. Only when you construct the theory in the Lagrangian, you'll find out that it's the same.
Is the standard model valid at all scales of energy?
No, this is a low energy effective theory. Low as in up to about 125 G.
So shouldn't that also be a parameter of the standard model, like up to where it is valid?
We haven't reached there yet. The only other scale we know is the Planck scale, right?
Yeah.
Okay. Maybe in your lifetime we will find something else, but in my lifetime it's unlikely that we'll find anything else. You guys should do some research in biology and prolong my life. What's the point in knowing all this particle physics? Don't leave us this subject. So I'm still trying to tell you what the standard model is, which is fine, because if we kind of define the terms of reference properly, people can of course study on your own. So the theory that is called quantum electrodynamics, we of course need to define what it is, define it in terms of the Lagrangian. What is the spectrum? What is the spectrum of QED? The spectrum we mean what are the particles that are present. We already said what they are, the electron and photon. And you can add muon and tau. You can also add quarks, but of course the problem with quarks is that they are confined and then it's a real problem how to deal with them. So the low energy spectrum of the strong interactions are not the quarks, but they are mesons and baryons. So there is something known as the spectral assumption that interactions do not change. Interactions do not change the spectrum, do not change it. Which means that it should be possible to isolate a free part of the Lagrangian and an interaction part of the Lagrangian. Now this interaction part of the Lagrangian has a coupling constant G, or let's say alpha, and if alpha is much less than 1, which is the case in QED, and it remains so until all reasonable energies, that an electron remains an electron. It doesn't get bound to something else, and it always stays an electron. So that's why this is such a simple theory. In contrast to quantum thermodynamics, this is a theory of strong interactions, which involves quark and gluon degrees of freedom. But the spectrum is changed by the interactions, and you end up with mesons and baryons. Okay. QED is a well-behaved theory, and nothing there happens. So what we will do is, we will look at some simple processes over here, and try to get the hang of what QED is as we go along. Okay. So this is based on an abelian gauge principle. Which will allow us to write LQED. And we can see the symmetry properties and implications. And then you can apply to some processes. But what is it that you want to see? What are the observables in such a theory? The observables in such a theory could be, for instance, the anomalous magnetic moment, A mu, which we had already mentioned the other day, G minus 2 at 1 loop. And in order to study this, you look at a diagram like this, and you extract from this quantity like a vector. You could also study processes like E plus E minus, go to E plus E minus. But here there are two diagrams which contribute to this. Two diagrams, and this is called Hava scattering. Simpler process, simpler, is E plus E minus goes to mu plus mu minus. Why? Because there's only one diagram. Okay? Why are there two diagrams over here? Because there's one which looks like this, and there's another which looks like this. So you'll have to add these two, and then you have to square this to get the cross section. Whereas here, there's only one diagram, like this. Square this in order to get the cross section. So one can look at these things and then E plus E minus, tau plus tau minus. In QED. But then I can complicate life for us, not only for myself, but for this, and we can do this in the full electroweak theory. Electroweak theory. Now, you people have heard all these things, and you have been in courses where you've done this. So there are two diagrams in this case. So this is with the photon, and this is Z naught like this. So obviously the result that you get will be different over here, and at very low energies the contribution of this is going to be very small, so we throw it away. At low energies it will be dominated by this. If group S is much less than mz, then we don't care about this. So we're still talking about the book of Need and Grossman. So after this, we'll have to introduce non-abelian symmetries. Why? I'm going to take a break here and ask you why you think we need to have non-abelian symmetries. No, this is not for the flavor sector. Yeah, also, of course, but I'm talking about for the moment non-abelian. So, thanks. One is for the flavor part with UG and swaps, and another is for the gauge sector, which has to account for what is the gauge sector of the standard model? Photon, then what else? W plus W minus and gluons. How many of them?
8.
Now, why do you think that there's only one photon over here in QED? Why only one photon? This is different from the Kathopanishad because here I'm asking the question and you people are giving the answer. So supposed to have been in the other direction. But anyway, why only one photon? No Kathopanishad, of course. No, you don't even read my WhatsApp. Like my daughter who deletes all my messages. Yeah. Okay. So why only one photon? See, why deletes my
Because QED is
WhatsApp?
abelian. Because QED is abelian.
And so?
So there are no color indices.
Okay.
So H could be one, there's only one generator.
Exactly. So we said abelian. So U1 is abelian and has only one generator. Okay. And what about here? See, the thing is, you're not going to say, oh, there's a U1 for this, there's a U1 for this, there's another U1 for this. It doesn't make any sense. So that would be so trivial that it is not a theory. Okay. So here you already say W plus W minus, which means that they're somehow sitting together, and then they have a cousin that is known as the Z. Actually, it's a linear combination. See, one more mixing. Gamma and Z actually mix, and one of them gives one combination is called the D, and another third one is called the W3. Okay? So actually, there is one more mixing over here. And what is that mixing? One more mixing. So there is a B and a W3 which mix together, a photon and a Z. And what is this mixing called? Hmm? Electroweak mixing. It's named after somebody. It's named after Weinberg. So this is called Weinberg. Okay? That's what he got his Nobel Prize for. Just one angle and you get a Nobel Prize. That's all. But unfortunately, all the angles have been used up. There is no way to create one. Okay. So the point that I'm trying to make over here is that these are not trivial products of U1s. There's more structure to it. That these get tied up amongst each other. And it's not like there are 8 U1s to give you 8 gluons. Okay, that doesn't make sense either. They all sit together to express some symmetry. And what is the symmetry associated with these guys? Okay, I'm going to ask you that. Electroweak and strong are based on certain symmetries. And the electroweak symmetry is called SU2 cross U1. It spontaneously breaks to Higgs mechanism to give you U1 of electromagnetism, leaving behind massless photon. However, MW, MZ are not equal to 0, and MW over MZ squared is an important parameter, and I'm going to ask you what is this equal to. Please look up Google and tell me what is MW and what is MZ. I think we already gave a number the other day. Okay? And just over here, the strong interactions are going to be 8 of them. 8 is a nice number that will already lead you to some nice symmetry. What's a nice symmetry? Why? Hmm? Why n squared minus 1? How do you know that? Many people telling me a lot of things. So UN is a group of unitary matrices. Unitary n by n matrices. Okay? How many parameters does a general n by n matrix have? General n by n. General n by n has 2n squared real parameters. What does the condition u dagger u equal to identity give you? It gives you n squared constraints. N squared constraints. Okay? So un has how many generators? Has 2n squared minus n squared equals n squared generations. Okay? What about SUN? Somebody mentioned SUN. What does the SU stand for? Special. Special means what? Determinant is equal to 1. But if determinant was not equal to 1, then what is the determinant of a UN matrix? No, wrong. It is a phase between alpha. Okay? It's a continuous part. So you have to get rid of one more constraint. You say this, that's how you get n squared. Since we are over here, and since all of you like mathematics more than physics, let us go over ON. How many generators does ON have? ON is a group of orthogonal matrices in n dimensions. Okay, real entries. Okay, what it means is that you have n independent planes in this space. space where you can carry out rotations and leave the length of a vector unchanged. Okay, that's what is meant by an orthogonal group. It is the set of all those transformations that leaves an n-dimensional real vector in an n-dimensional space, leaves the length invariant. Okay, so what that means is that you take a vector and you turn it into another vector, and the length remains the same. How many such ways are there of independent ways of rotating this? Any arbitrary rotation can be expressed as a combination of independent increment, infinitesimal rotations exponentiated in order to get the result. Okay, so that means that you have to look for a plane in this n-dimensional space, and how many such independent planes are present? Any two vectors, you can always find it to lie in a plane, right? So,
N into M.
NC2, okay? Correct. So that's how you get n times n minus 1 by 2. You guys are all genius level. You don't even need me to teach you. So in future, you teach yourselves, okay? Brings, of course, assuming that he's listening to what I'm saying. So n times n minus 1 by 2. But SON, so there, as Pratibha said, the determinant can be plus or minus 1. However, SON also has the same number of generators. It's not a continuous generator. So that's like n times n minus 1 by 2. Okay, so here you get 8 generators. Okay, now one of you is going to look up Google and tell me what are the masses of W and masses of Z. Okay. Yeah, go ahead and write it down. Both the central value as well as the errors. Are you sure it's just 0.4?
80.377.
No, you should write the whole thing. See, it doesn't make sense to round it off to 4 if you're going to give those errors, right? See, I have to track you guys with each of these. Here's an excuse, it's jet lag coming from Delhi and all that. So why did I ask you to write this in so much detail? Well, I may be mad, of course, that is one explanation. It's also a simple explanation, but not the right explanation. So, why did I ask you to write this? That too, all the significant places, and I want you to think about why are the errors like this and not something different? One of you has to explain to me the significance of what you've seen over here. Because I'm going to lead you up to experiments from which these numbers are determined. Okay, so you tell me, this is known to how many significant places and why is? So here you see the uncertainty is an order of magnitude less. Okay, now I'm going to ask you why is that? Why is this so much better determined than this?
The range is into a lot of other particles, so you know the deviation. It's easier to calculate if they give it and then find it.
This is an experimental number. Nobody is calculating anything. Okay, this is determined from an experiment. Which experiment? You should find out. Homework problem. Okay. Now that even because the test matches are over, now we can devote a little bit of time to physics. Very boring test matches, I might add. Okay. So this number comes from an experiment that is known as LEP. What does it stand for? Large positron collider. And where was this? CERN. And it was, as the name suggests, it collided electrons and positrons. Okay? And it was colliding at the Z peak, the center of mass energy. For a very long time, most of the experiment was done at the E plus E minus center of mass energy corresponding to the Z mass. Okay? Now, any unstable particle, it comes into being and then it decays. So, what can you say about the line shape of the cross section? So, if there is a resonance, why is this a resonance? We already said that it is a gauge particle, and we already said that Jp of the photon is 1 minus, right? J of the Z is 1. But we don't write down any parity for this because of the interactions by parity, so we don't write P. So this J equals 1 means that it is a resonance in the angular momentum 1 channel, which means that if you collide electrons and positrons and line them up very nicely, then you have a very high probability of producing this particle. So if a particle is produced, what are the characteristics of an unstable particle? What are the properties that you have to define for an unstable particle? The mass of the Z, and the decay rate, gamma Z. Okay? So which means that you will get, as a function of root S, if you have a cross section, let us say for E plus E minus goes to E plus E minus. As you vary the energy, when you reach the Z mass, get a bump like this in the cross section. And this here is, the width here is related to, it's the width. So because this is a resonance, you can tune the beam energy very accurately. You can actually measure the width, measure the mass and the width very well, which is not the case when it comes to the W. Okay? So later, at lab 2, which was at a higher energy, lab 2, can someone check what the center of mass energy was at lab 2? I think it is 208 GeV. Root S equal to, I think it was 208 GeV. You had copious production of E plus E minus 2, W plus W minus 2. But this is not a resonance, okay? So that is why the corresponding measurements of the mass of the W are not as accurate. So whenever you people run into some number, you can think a little bit about why are these numbers what they are, what is the experimental situation in which this thing was measured. What's the energy?
Yes. 208.
Yeah. They are still not completely dead. 89% dead, but the last 11% is still dead. Okay. This was a very nice energy, but it was hoped that the Higgs would already be discovered at this configuration, but it was not. Why? What's the mass of the Higgs?
125.
Mass of the Higgs, 125 GeV. Maybe it was produced in lepto, but it's definitely not detected and one could not say that it was actually produced. What happened to this lep? Any idea what happened to that? Hmm?
The Newton accelerator for Large Hadron Collider.
Correct. So lab was closed down, and the same tunnel has now become LHC. The large has remained unchanged, this is the hadron collider. What does it do? What does LHC do? Hmm? Produces black holes. Not quite, but anyway, what does it do? What does it collide on what? Collides hadrons, obviously. What kind of hadrons? Hmm? Protons on? Why not antiprotons? Now it would be very nice to collide protons and antiprotons, no? Electron positron collider. Maybe you want to have a proton antiproton collider. That's what was done at Tevatron in Fermilab. Fermilab. Proton antiproton. Why didn't LHC collide protons and antiprotons?
Antiprotons are unstable. Yeah.
Not unstable.
And
Partons, because they are hadrons, so they have internal structure. So instead of annihilation, actually interaction might be more useful.
If it was possible to collide protons and antiprotons at Fermi lab, I'm asking you why it is not possible to collide protons and antiprotons at LHC. Because it's very difficult to have a large number of antiprotons, not because they're unstable, but it's very difficult to have a large number of antiprotons, okay? Because to produce antiprotons and to trap them and to keep them without their getting annihilated and disappearing and so on, if you want a large luminosity is another useful word, luminosity, okay? Center of mass, luminosity, these are all words you have to know, center of mass energy. Tomorrow when you're in some interview and you're asked what is the luminosity of the LHC, you have to know. If it is antiprotons, the number of antiprotons that are available are so small, then you cannot have very luminous beams. That's why it's photons and protons. But this is not the only mode. There's also a lead on lead mode. And this is done mainly by the Alice collaboration. Now I have to tell you all these stories because without this motivation, what is the point in studying this kind of model? Okay? What are the experiments and detectors at LHC? What were the detectors at lab? And what are they all good for? And actually, the LHC colliders, detectors, yeah.
So we said that we don't have more number of antiprotons, since it's difficult to have, then how do we have more number of antiprotons to find that?
They had, theirs is much less ambitious. The luminosities and so on are much lower. Okay?
But in LHC also then we can have that less number of antiprotons than we have.
There's no advantage. See, whenever you're designing some machine, you have to have certain goals in mind. Your goal may be a certain number of events, and you don't want to be limited by the luminosity. Now, Fermilab experiment is very old. At the time, they needed it. What the Fermilab did many amazing discoveries. They discovered the top quark. They discovered maximum B mesons, all kinds of things. So it depends on your physics goal. Okay. Here we and all of us, mankind, we wanted LHC to have as many events as possible. Okay? And we also want to probe beyond the standard model. We want to produce supersymmetry, we want to produce extra dimensions, we want to produce black holes. So to do all this, you need extremely intense beams. And you could not reach that kind of intensity if you had anti. Now this is what I remember, but it's a very good project for you to read and educate the rest of us why they selected proton and not proton antiproton. The earlier CERN experiments used photons and antiprotons. The famous STS collider, which discovered the W and the Z, 1984, an experiment called UA1, UA2, UA1, underground area 1. They stupid sounding names, but that's the kind of names they had. So UA1 discovered W and Z. So at LEP, they had 4 important detectors called Opal, Delphi, Aleph, and L3. They also had another smaller experiment there, which was called, it was a monopole detection experiment. Monopole detector. At LHC, can somebody tell me what are the experiments? I just named one of them, it's still there on the blackboard. Alice, CMS. India is a member of CMS. IISc is also part member of CMS. Anything else? You people know Atlas? See, I'm just not consulting my notes. You have to know. Atlas, then LHCb. Then there are other smaller experiments, LHCf. There's one called Totem. There's one called Noida. Okay. CMS is the compact muon solenoid. It's not particularly compact, it's an enormous uh, detector. Atlas is even bigger, and Atlas stands for A. Something is a solenoid. What's the opposite of a solenoid when it comes to magnetic systems? Right. And LAS, LXC, correct. Right, like that. So this is A, NSC, ion collider. And here B, this is specialized to study B mesons, B quarks. And here the F stands for forward. This stands for total cross section. And it is used to calibrate the detectors. And this is again a monopole score. So at these experiments, everything we do so far has been to test the standard model to higher and higher accuracy to see whether we are able to see anything which suggests a breakdown of the standard model. And sadly, there is nothing so far to suggest that the standard model breaks down. It's probably because we have not reached high enough energies to do that. The highest energy reached so far, E plus P, highest energy is 13 eV. I think it's slightly higher now. 13.6 eV.
What about G minus?
What about it?
Doesn't it imply standard model based on?
No, I don't think so, not yet. So G minus 2 experiment. This is a Fermilab experiment. Okay, so there's still discussion. So this is only a number, some, should we say, attention. So, having said all these wise words, I should go back to what we want to say about non-abelian symmetries. So, QED is a prototype of gauge theory, very simple. We can work out exactly what the Lagrangian looks like, probably in the next class. But now let's see what non-abelian theories look like. So, abelian. So, let's call this Maxwell theory. Maxwell. And let's give the name one of this. And over here, the Lagrangian will contain the electron, and it will contain this. And then it will give you the interaction of psi with mu. And also, we have to promote mu to a dynamical degree of freedom. How do we do that? Dynamical degree of freedom. If you didn't promote it to a dynamical degree of freedom, it would mean that it's an electron moving in an external electromagnetic field which has no dynamics. But if something needs to have dynamics, what is it that you need to do for that degree of freedom? You have to introduce derivatives, right? Dynamic means what? Moving. Something moving. And in order for something to move, it means that there must be derivatives with respect to space and time and so on. Okay? So then, what you do is F mu nu Maxwell. Can somebody tell me what this is? Now, all of you know this covariant language. So this is why it has become dynamical. You have an F mu nu like so. But this is not all. You have to add this to the Lagrangian L, and this, the Maxwell part of L, is something that is constructed from this, and this would be a minus 1 by 4 F u. So this is it. QED. There is a psi bar like this, E slash minus E slash psi minus 1 by 4. What in the world could be simpler than this? And once you have a Lagrangian, of course, you know that in order to solve this particular theory, you have to break this up into a free part, and an interaction part. Right? What's the free part of this? Oops, this is wrong. The D slash already has this. Sorry, I'm just, I may have some eyes missing here and there. I think there's an eye over here. But please check this. Okay?
I should be ID.
Like here. Is this okay? Good to have some conscience keepers over here. So the free part over here is this psi bar I D slash psi minus 1 by 4 mu. And the interaction part is I E gamma mu psi bar psi. Okay? And in order to do perturbation theory, what do you need? Perturbation theory. What do you need? You need the free field equations. From which you get the propagators. And here you can easily figure out what they are. These are the propagators. So, and the interaction part will be the vectors. Why should this be the case? You people have studied all this in your theory courses. You know, you remember, should I give a small recap on why the theory is solved in this particular way? Now I'm going through all this very slowly to motivate how we may do something corresponding for the non-Abelian theories also. We have to be able to write something similar, but of course you won't have one species of particle, there are more than one species of particle. So that there's a non-trivial symmetry as far as the matter part is concerned. So whenever we say something like psi, we speak of matter. When we speak of matter, we speak of fermions, scalars, like the Higgs. Whereas when we talk about force carriers or gauge bosons, we don't call that matter, we call that the other part of the theory. This is, of course, QED, but you can also have scalar QED. Scalar QED, where you have, let's say, a complex scalar field phi and phi star, in which case your L will be phi star like this, minus m squared. Star minus 1 by 4. And what is this d mu over here? It's the covariant derivative. We are still thinking of scalar QED. So this d mu here is scalar QED. So once again, this will give you the free part, and then there is an interaction part. And the interaction part will have two vertices. Why will it have two vertices? Because when you work this out, you get a cubic piece, you get a quartic piece. Okay, so then you will get something like this over here, which is a cubic part, and then what is the quartic part? Like this. So you will get two kinds of vertices. This will be G or E, and this will be. Now everything that we have done so far is still Abelian symmetry U1. And the question is how to promote this to a more complicated or a richer theory. And what is that richer theory for? If this U1 is promoted to something else, some other G with n generators, and this theory is called Yang-Mills theory. Yang-Mills. It will look very similar, obviously not the same, but this part of it is going to be much more complicated because of the structure of non-abelian invariants, also which you have done in your course. But there's another technicality which has to do with parity violation and the presence of fermions. Okay. I'll have to introduce parity violation a little later, but then you will have fermions which are of two different kinds. Fermions can be chiral fermions, chiral or vectorial fermions. Vectorial. So this will be in weak interactions, whereas this is in UCB, because these are parity conserving. Parity and all these theories are quantum field theories in which coupling constants are not constants but are called running coupling constants. Running coupling constants due to interactions. And these satisfy or evolve via something renormalization equations, RGE, or renormalization equations or renormalization evolution. Okay. So there are two kinds. So U1 electromagnetism, coupling constant E increases with energy and eventually meets something called a Landau pole, where it diverges. And what we do is we compute the beta function, in loop expansion. At one loop, you will see that this thing actually diverges. So this is for the coupling constant, but the other parameters also run, and then you have to compute something known as the anomalous dimension for dimensionful parameters such as masses, okay? And any other quantity of interest here. But that's all not part of this course. So that's some other course. So QCD on the other hand, QCD on the other hand, is a theory of gluons and quarks. And coupling constant diminishes as a function of energy. Function. Not for all. When number of flavors is bounded by some number, and such theories are called as in the standard model at one loop, you can compute the beta function. The other key notion which I mentioned previously, which also appears as a chapter in Grossman and Neal, is spontaneous symmetry breaking. Spontaneous symmetry breaking. This, by the way, shows up both for global as well as local symmetries. So when global symmetries break, it gives rise to something called Goldstone bosons. And these are very useful for understanding the low energy spectrum of the strong interactions. And we will talk about this in the next class. Useful for studying low energy spectrum. What do I mean by that? Low energy spectrum of strong interactions. Hmm?
100 TeV.
No. When I say the spectrum of the strong interactions, what am I talking about? No, that's not the. That's the fundamental degrees of freedom. Okay, in the co-access. We are talking about the spectrum. What I am made of, what you are made of. What are you made of? Electrons in the outer shells, but deep inside there are nucleons, protons, neutrons. Okay, those are the low energy degrees of freedom. You're also made of protons. Don't be shy. We all are. Okay? So we are all made up of these things, which is the low energy spectrum of the strong interactions. Okay? So things like protons, neutrons, and other strange counterparts. So in order to classify these, and the force carriers between protons and neutrons are, don't tell me gluons. Gluons are microscopic degrees of freedom, but effective degrees of freedom, which keeps protons and neutrons together, are ions and so on. Phi plus, minus, phi 0, k0, k0 bar, k plus minus, eta, etc. Now these guys are the Goldstone bosons of certain approximate Goldstone symmetries, approximate Goldstone bosons. Now, if you really want to understand the standard model, there's no way of escaping these things. You can't just keep convincing yourself, I'm only going to think about the Higgs and so on. The standard model actually is most effective at low energies, at day-to-day energies. Okay? So we have to know about the relations and the implications of other symmetries of the QCD Hamiltonian. Not the gauge part, but other global symmetries associated with the fact that the U, D, and S quarks are very light on the hadronic scale. So that gives rise to approximate symmetries, which are known as chiral symmetries, and where these chiral symmetries are spontaneously broken. Then there are approximate Goldstone bosons, pions, kaons, etc. And there are very beautiful relations between all these, implied by the mathematics, by the group theory. Okay? So it's not accidental that there are many of these relations, but it is actually predictions of the approximate theory. And you have to be able to really get on top of these things. Then you can, of course, make life very simple and talk only about the leptonic standard model, which is what these guys do. And then you include the quarks and get the standard model itself, at least at the level of the Lagrangian. And then eventually you have to discuss a lot of this flavor physics associated with different quark flavors, atomic flavors, etc., etc. And then our friends also have QCD at low energies. So these are the rough collection of topics that we'll be looking at. And then they talk about electroweak precision measurements. And then the possibility of looking for flavor changing neutral currents, and then also neutrinos. Now this is all very ambitious, so God knows how much of this we will actually do, but some of these can become topics um, for your discussions. So there has been a really heavy 80 minutes. How are you all doing? We are in class again, beyond the standard model. And analytic continuation from the standard model beyond the standard model. Okay, so I'm going to stop the lecture over here and let's take some questions. And I'm not going to let you out of this room until these people ask me some questions, which I can't answer, of course. Questions? Everything's clear, crystal clear, absolutely no problem. Yes? If only you had come to the last class, you could not ask. You guys always make these incorrect assumptions. If the calendar says January 1st, it means January 1st. It doesn't mean January 6th. Okay? Yeah, so the idea was motivated by the COVID era that we will have breakout rooms and we'll have like groups of 3 depending on, and then we work together, pick a topic, rather I pick a topic, and then people work, write a paper, jointly make a presentation, and you educate each other and educate me also. Okay, more questions? Mr. Fugain, any questions? He has no questions. Everything's so clear.
So pions are a result of local symmetry breaking?
Global.
Then what do we get from local symmetry breaking?
You get gluon, the mass of the W and mass of the Z. So the symmetry breaking is associated with the electroweak sector of the global symmetry. So if you read Weinberg, his famous paper, the most highly cited paper in particle physics, on a model for leptons, he explains that he was thinking of breaking global symmetries, local symmetries, and applying it to pion physics. And one day he was driving his car, a red sports car, I believe, and then he was parking his car, and then it just suddenly occurred to him, I'm applying the right idea to the wrong model. Okay? And that's how he proposed his electroweak symmetry breaking, and he has all the relations there. He has all this fixing. It's really incredible. It's only about 2 pages long. You can have a look. So, spontaneous symmetry breaking of a local symmetry is applied to the electroweak sector, Higgs mechanism, which gives masses to the W and the Z, and leaves the photon massless. In the strong interaction sector, it's also an SU3, okay? That SU3 of flavor has nothing to do with SU3 color or QCD, okay? Repeat slowly after me. It has nothing to do, okay? That is SU3 flavor associated with the near masslessness of the 3 lightest quarks. Okay? That's called the chiral symmetry. Why? Because in Tamil, chi is hand. Chirality, okay? It's also the same word in Greek, chirality. You know, all this sugars, dextro, and same chirality. So it's this chiral symmetry, which is a symmetry of massless QCD, is spontaneously broken by the QCD vacuum, not the Higgs vacuum, not the, but by the QCD vacuum, which generates Goldstone bosons that are the pions, kaons, and the theta. However, it's not an exact symmetry, it's an approximate symmetry because mass of the pion not really is 0, it's very small, but it is no, non-zero. Still, the symmetries, the memory of the symmetry is still there, and it implies many relations, such as the mass of the pi plus is almost the same as the mass of the pi naught. What's the mass of the pi plus? Quick, Google. You people still have 7 or 8 minutes. पूरा पैसा वसूल करना चाहिए. One 139. And there's a reason why I'm asking you. What about mass of the neutral pion? Neutral pion.
134.9.
135 roughly. So the neutral pion is slightly lighter than the charged pion. Okay,
But eta is much heavier than pions.
that's the topic of the next class. Or I give it to you, you read it and you come and read the lecture. So that's because the eta has the S quark. The S quark is much heavier than the UND quarks. Okay? So the symmetry associated with all the 3 quarks is not as good as the 2 lightest quarks. 2 lightest quarks, very beautiful symmetry. Okay? So in the pure pion sector, it's a very nice symmetry. Whereas in the sector that involves the pions as well as the kaon, in the eta, it is not as good. Nevertheless, it is still pretty good, and it gives many, many relations which are very useful, which we will look at in the next class. Okay. LCS. That is flavor changing neutral currents. Why is that? Because an electron interacting with the photon remains an electron. Okay? So the neutral current does not change the flavor, it is flavor diagonal. On the other hand, the charge current changes the neutrino into a charged electron. Okay? So the charge current changes the flavor, whereas the neutral current in the standard model does not change the flavor, except at higher orders. 2 loop diagrams can generate. Okay? So called penguin diagrams they can generate. But that is understood. It's a higher loop effect. However, if you saw flavor changing neutral currents at an appreciable rate compared to what the standard model predicts, that is physics beyond the standard model, about which you'll hear in 5 minutes. Okay? Any more questions?
When you were talking about approximate symmetry,
Yes.
in what sense are they approximate? The mass.
This Goldstone boson is expected to be absolutely massless if the symmetry was exact. There are no terms in the Lagrangian that violate the symmetry. So you say a symmetry is exact if the Lagrangian is invariant under certain symmetries. Okay? However, it may have a part, which is the main part, which is invariant, and the small interaction term, which is not invariant. Now, this you do in quantum mechanics all the time. You have a rotationally symmetric hydrogen atom that you immerse in a magnetic field that is pointing always in the z direction. You never know why it never points in the y direction. It always points in the z direction. Stupid magnetic field. Nevertheless, you can have levels which split. Even though the symmetry is broken by the presence of your magnetic field, however, it's a small perturbation on the unperturbed Hamiltonian. If you have an unperturbed Hamiltonian, your Hilbert space of states is still spanned by the spectrum of the unperturbed Hamiltonian. Yet, you can compute the changes to the energy by taking those and computing it in perturbation theory. Right? The interaction part which violates the symmetry. Nevertheless, you use the same eigenbasis as of the unperturbed system. It's exactly what you're doing over here. You have a system where if you switch off the quark masses, it has this full, beautiful ideal symmetry. Okay? Then you have a small term which violates it, which is the explicit mass term. There's also, unfortunately, a spontaneous symmetry breaking. So if you see the vacuum is a very complicated beast. It has a small explicit breaking term, and then it has a spontaneous breaking. Together they conspire to give a non-zero mass to the pion. Okay? That is what condensed matter guys call a gap in the theory. So again, you study the unperturbed Hamiltonian, and then you compute all exchanges. Okay. Okay, so until 46.5 hours from now, have a nice day, and I should tell the night to stop recording the lecture. Okay, yeah.
We can think in quantum mechanics because we can always think it has some discrete symmetry. And supposing the symmetry is closed, so it does form closed.
Yeah.
Then I can think of the number of degenerates of the system if I solve for the spectrum as being somehow related to the cardinality.
Yeah, sure.
But in this case, as I discussed, whatever is happening or whatever that is called, so the S3 symmetry is taking to U1. So can I think of the degree of degeneracy due to the splitting of energy levels as somehow related to the lower number of generators in U1?
Yes, there are all these things. The Goldstone theorem tells you exactly how many such classes Goldstones you get in terms of the original symmetry and in terms of the residual symmetry. Okay? NG minus NH is the number of Goldstones. This is a backward